Okay, I thought I'd do a little video here on couplers. They're kind of strange devices, and they can be confusing, especially the way they're labeled. We talked about grounds being labeled, whether a ground is really ground or not. Why do engineers call them grounds? Couplers are kind of weird too, because there's something called input and output. But you could actually go the other way as well. You can have the in go into the out and the out go into the in. I'll show you that it doesn't matter. And then there's this funny little connector over here, and this one's called forward coupling. This one's called coupled port. This one is called CPL couple. And this one has two weird things on it. So anyway, let's talk about what the thing does, basically. Okay, we'll just do this in general terms. This is not an RF class. This is just, you want to use couplers. So there is an input connector. We'll use this one. There's an input connector and an output connector, okay? And inside, that's just a transmission line. It's just a short. And if you put things in here and measure them here, they come out. And if you put things in here and they measure them over there, they come out. It's just a wire, okay? And so you can go either way, all right? So in some instances, and I'll show you a measurement that I'm going to make, I'm actually going to be putting the signal source in the output connector. We're going to run it backwards, and there's a reason for that, and I'll show that to you, okay? So in and out. And then there's this thing called couple. What is couple? Well, couple is a funny, we'll call it CPL. It's this funny little thing here, and what it does, it's a one-way valve. Okay, you think about this as a hose. Water goes this way, okay, but it won't go into this one here. This is funny one-way valve. But if you put water in this direction, it comes out. So even though this is a wire, you can go either way. The coupled port is that it only sees some of the water from this direction and none of the water from that direction, okay? And how much? It's not very much, okay? It's only a percent or two. So how much comes out is usually specified in dB, okay? So this particular one is called a 20 dB coupler, okay? 20 dB, that's 1/100th, right? So 1/100th of the signal going in this direction will come this way. 99% of the signal will continue on its merry way. But in this direction, 100% of the stuff comes out the other side, okay? All right. So that's the coupling, okay? So let's measure a couple things, and then we'll talk about some other things. All right, let's go over to let me move things around here, get my drink out of the way. We're going to be using my spectrum analyzer to be doing all these measurements. All right, and I am going to preset the instrument. I'm going to set the frequency, a start frequency of let's say 50 megahertz. And we'll do the stop frequency of, let's say, 200 megahertz, 200 megahertz. Okay, there we go. And we have a thing zipping around, okay? And there's nothing coming in, okay? And what this says is I can only measure things down to minus 60 dBm, okay? This is minus 50, minus 60, 65. So my noise floor is about minus 65 dBm, okay? Oh, okay, just remember that. Over here, we're going to have our tracking generator, okay? So let's turn the tracking generator on. We'll turn him on. We'll set him to the level of 0 dBm because those are nice numbers. So he's outputting 0 dBm, okay? So we're going to use a little female-female adapter, and we'll connect the two together. And we will set the amplitude reference level to 10 dBm so we can see it. So right there at 0, that first line there is 0 dBm. So you can see that we have a nice 0 dBm going through, okay? And so let's take out our little adapter here, and we will connect the coupler, all right? We will put the in to the in, or the out to the in. Anyway, the tracking generator is going into the in, and our measurement, is going to be on the out. So let's see what that looks like. And look at that, just a piece of wire. Whatever goes in comes out, okay? And then let me show you backwards. I'm going to be going in the output, okay, and I'm going to be measuring what comes out the input. I know that seems strange. That's why these things are confusing, the way that people label them. There you go. See, it's a piece of wire. Input, output, output, input. It doesn't matter. Okay. So the other thing that we want to do is, remember I told you that if we were going in this direction, okay, we'll go in the in, okay, there's going to be something coming out this side, okay, we measure that, remember we measured that, I'll do it again, measure that, it's 0, but what comes out the coupled port? Let's put in, the thing that comes out the coupled port is minus 20, okay, so I said that this is specified with a coupling factor of 20. And so we're here at minus 20 because we're inputting 0, but it's what's coming out is 1/100th of a signal that comes out over here, okay? And remember I told you that it was a one-way valve. And if I put the in into the out, you say, wait a minute, it's coupling that too. Well, that's for a reason. So we need to talk about this. Why is this measuring just as much as the other way around? Okay, let's go back to our piece of paper. Okay. All right, so I'm putting a signal into the output. It's coming over here, and there's nothing connected here. So it sees an open. And what happens is 100% of the signal gets reflected. And so 100% of the reflection goes into the coupling port. Now, if I put a 50 ohm load here, then all of the energy will go into the 50 ohm load, and we won't have anything going backwards, okay? So let's take a look at that. Okay, so I'm going to put the 50 ohm load on it, and bang, there we go. Okay. Now we need to talk about this a little bit, okay? So you can see that we're down here at minus 50 dBm, okay? We were at minus 20 if it's full signal, but now we're down at minus 50. Well, what does that mean? Does that mean that none is coming out? Okay, let me disconnect the measurement. And you can see that, it went down a little bit, remember? We were around minus 60, and if I put this on, the level goes up just a tiny bit. Now we can help that out with a spectrum analyzer. We can make our noise floor a little lower. We can set our bandwidth here instead of automatic, we'll put it in manual. So I've put it in 100, it was at 1 megahertz resolution bandwidth, and I put it in 100 kilohertz bandwidth, and now our noise floor has dropped to about minus 60 right now, okay? And now if I plug in to our coupled port, it's rising up to about minus 50, okay? So there's about a 10 dB signal over ground, over noise, okay? It's 10% more than noise, than the noise level, okay? Now, when you're making measurements, you have to make sure that the noise level of your instrument and the what's called directivity. Directivity is how good is it in the reverse direction? How good of isolation? Sometimes you'll hear it called isolation as well, okay? So in our picture here, what we see is that there's actually a little bit of this direction coming in. Just a tiny, tiny, tiny bit, okay? How much? Well, we can measure it. We can look at the data sheet, look at directivity, but we'll just measure it, okay? So if we put on our load, let's see here, we want to go, make sure we do this all right. I want to measure this correctly. We are going in, coming out. All right, so we are measuring about minus 50. What is the total signal? We know the total signal is about minus 20. That means that there's 30 more dB of loss, at least. So we can say this has a directivity or an isolation of 30 dB. it's 30 dB less than the full signal, okay? Which means that if we want to use this as a one-way valve, we have to remember its limitations. Its limitations is only 30 dB. We can't measure anything bigger than 30 dB because of this isolation problem with this particular thing. Okay, but we can get down to minus 50. Now we have to keep all these numbers on our heads and everything, right? And so if we want to use this as an SWR bridge, what we do is we open the input. Now we're getting the full signal back. We're getting our 20 dB signal, or minus 20 dBm signal back, okay? And what I'm going to be doing is everything I've been talking about so far was in dB millivolts, okay? A lot of engineers get sloppy, myself included. They'll just say dB. dB is a relative measurement. It has no units. It's just like a ratio. dBm is an absolute measurement. It's a dB reference to 1 milliwatt. But if we want to measure things like SWR, return loss, and things like that, that's a relative measurement. That's just a ratio. So we need to zero things out. So in our tracking generator, we can say we want to store the reference and normalize. And now this is normalized so it says 0, that whatever's coming in and bouncing back, and you see 1/100th of it, we're saying that's 0. And now when we put our 50 ohm load in there, it dropped down to minus 30, okay? So that's the best way to measure this directivity, is to first zero it to 100% reflection, which is without a load, and then measure it with a 0% reflection, which is with a load, and you still see that there's 30 dB sneaking through, and that is the directivity of the thing. But we can use this device now to measure return loss all the way up to minus 30, because the noise floor is good there. We can do that. So if we take a antenna as our test subject, and we screw it on, and it doesn't work. What happened? What did I do? Oh, that was really, really dumb. My start frequency is 150, not 50. So let's go back to 50, see here. We need to start over. Okay, so I'm going to do a preset. Whenever you get into trouble, you should really do a preset and start over. Our start frequency we want to be 50, not 150, 50 megahertz. And our stop frequency we want to be 200 megahertz. Now we can see this antenna, which is at 144, okay? So there we go, all right? We are going to turn the tracking generator on. We're going to set it to 0 dBm. Okay, we are going to turn it on. There's our minus 20. We're going to zero it. We're going to normalize it. We're going to set our reference position up here to 90. So now the line's up there. So now anytime we put something on it like this, this 50 ohm load, we're down here at minus 30. So it's a very nice load. All right. Now if we put a antenna on, which is what I wanted in the first place, there we go, boom. Now we can see our antenna, okay? And our antenna is going to be very susceptible to things that are around the lab, and if it's pointed at something or there's a ground, anyway, you can see here that we can get a very, very nice dip measurement, okay? We should be able to get down to at least minus 30, okay? That's where our noise floor was, remember? And so most of the time when you're measuring antennas, you really need to only go down to minus 25, maybe minus 20 is just fine and dandy. I would say minus 25 is probably a really, really nice noise floor to have, or dynamic range, however you want to call it, is a noise floor or dynamic range. But you need to get down to about minus 25. This particular setup will get me down to about minus 30. And you can see here, we can actually make some measurements that's kind of sneaking in there almost at minus 40 for this thing, right? It's probably noise and stuff, but it's right around minus 35 is where this thing bottoms out. So yeah, there we go. we'll go back to our, let me put the 50 ohm load back on. And yeah, our 50 ohm load is looking good, okay? All right, so what did we do just then? We created our RF source and we put it in this direction. We put it in here, okay? And then we had an antenna screwed onto the connector here. So here's our antenna. And if the antenna was a perfect load, then all of the energy would go into the antenna, but the antenna is not a perfect load. And so a little bit gets reflected back, okay? That gets captured here, and we can measure it here. We calibrate by reflecting back 100% and calling that 0 dB. And then we put on the antenna, and we measure minus 30 dB, and we say the return loss is 30 dB, okay? And that's the way it works. Now, you might get into trouble with your device, and I'm not talking about antenna, but I'm talking about a coupler, okay? You have to make sure that the coupler is not too bad. Remember, we had a 30 dB of isolation in this particular coupler. That's quite good. I think you can get 40 dB ones if you pay money. There's also the matter of the input, the 20 dB coupling. The 20 dB coupling really shouldn't be an issue whether you get a 10 dB coupling or 20 dB coupling. I think the 10 dB coupling ones are a little bit worse for isolation. And so I think you get a little bit better isolation if you have some amount of loss in the coupling. Now, what about some systems where we want to measure this reflection, and we also want to measure this reflection, okay? And you can do that. You can have two one-way valves. One-way valve that works in this direction, and another one-way valve that works in this direction, okay? And that's what this is. This one has two ports. It has this one, which is the one-way valve from the input port, and this one, which is the one-way valve from the output port. Now, most of the time, there'll be a 50 ohm load attached to this one. Now, it's not removable either. You can get them where you can probably just remove this one. It's painted over, but you could probably remove this one and use it, but some just come with both sides open if you want to use it that way. And the reason that there's this one over here is you need to keep everything symmetric. Whatever you do over here, you kind of need to do over here to keep everything happy, okay? And so they make this little coupling thing here. I'm not going to go into how they do that. But this funny little one-way valve thing over here, they put another funny little one-way valve in over here, and they terminate it with 50 ohms, and then everything is happy, everything is balanced, and everything is happy, and you can use it for good measurements and stuff. But if you see something like this and there's no little bulge over here, well, that 50 ohms is in here, trust me. It's in here. It's just that they don't build it this way with this lump over here. This is the same way. It has... It only has one connection, and it's next to the input port. And yeah, there's none on this side, but trust me, there is a 50 ohm in there.